ceramics, and we have seen how these ceramics are produced. We also talked about it in the exercise. Today, I just mentioned that there are several positions where there is soldering or brazing interconnect, and after one process, the next process must have a lower temperature in order to avoid remelting of the previous soldering or brazing. And now one important material for soldering is used here in order to attach the lid on top. Maybe first a small discussion. To which surfaces can we solder or braze? What is necessary that soldering or brazing is possible? Yes, so, sorry? Yeah, one thing is important. It is a metal, and it should be a metal that is wettable, and wettable means there can be there is no oxide. So wetting typically builds up a metallic bond on top, and so metallic bond means free exchange of bonding electrons or free electrons. And one very good method is also if there is a possibility to build an intermetallic compound between the soldering metal and the surface to be soldered. And here we can see the surfaces are typically nickel, but the finish is gold. Both nickel and gold are solderable materials, and the metal we use is, in that case, gold tin with 80% of gold and 20% of tin. What is important here, we have the phase diagram, and that shows us that pure gold has a melting point of 1063 degrees centigrade. So pure gold means we have 0% of tin and 100% of gold. When we increase the amount of tin in the gold, the liquidus temperature, it decreases significantly, having 20 atomic percent or 13 weight percent of tin in the gold already lowers the melting point to 500 degrees centigrade. But that is not useful using such solder material, because the solidus line is down here at 280. That means if we have such a composition, we will not have a melting point of 500, but we will have a melting range of 500 to 280. And in that way, it is better to go to that minimum point. How is that point called in the phase diagram? What is it? The point of minimum melting temperature, while at both compositions to the left and the right, the melting point or the liquidus is higher. That's a so-called eutectic point. And so it's very convenient to take a composition of roughly 20% of tin, 80% of gold, because here we have two advantages. One advantage is the melting point is the lowest we can have here in that range, and the second is it's a unique melting point. That means we do not have a range, but it's much better for a good process to have one well-defined point where it's consolidating or where it's melting. In that way, sorry. Sorry. In that way, we can see another eutectic. That eutectic is on the side near the tin. It is at 217 degrees centigrade. Why don't we use that eutectic here? What could be reasons not to use it? Yeah. Sorry? No, there are two reasons. One is it's not high enough, the melting point, because here we want to have such a melting point around 300 degrees centigrade. The second reason is there are other alloying elements which we can put in, which have the same effect. For instance, we can put in silver, and silver is significantly cheaper than gold is. So taking tin silver, for instance, we will later on see it, or even we can use tin copper or tin silver copper, would have the same effect and same melting point. And in that way, yes, we take advantage of that point. The phase diagram is quite complex because in theory, we have quite a number of phases. We have the gold phase, which is a phase-centered cubic. We have that theta phase, that's number 2. We have that gold tin phase, that's number 3. We have gold tin 2, that's number 4. We have gold tin 4, which is number 5, and we have the tin. So in that system, depending on the overall composition, we can have 6 different solid phases, and there is another phase which can exist, that is the molten phase. So in fact, that phase diagram exhibits 7 phases, but simultaneously we can only have 3 phases, like here on that eutectic point. When it is just melting, we can have the theta phase, we can have the gold tin phase here, and simultaneously there still can be some molten material, and in that way, at that eutectic point, we can have 3 phases. Okay. So that alloy is very important. Also, the interconnections are really strong. And another effect that is very important is we can make hermetic interconnections. Okay. Now, finally, see some other types of packages. That is a type I first found in literature before I found it in reality. That is a ceramic package that is injection molded. So we know about injection molding process, and we have seen that normally we take thermoplastic materials which melt. But what we can also do is we take some kind of thermoplastic material and fill it with a high degree of glass and aluminum oxide. In a way, when it is heated, it will become deformable. And in that way, we can either press or injection mold such a green material into a form, into a mold. When it cools, we take it out, but it's not yet finished. It must be fired afterwards. And in that way, because injection molding or also just deformation by pressing are really cheap processes where we can produce very many small parts simultaneously in one shot. We can produce the body of a package and the lid. Both are of same material. And so there is it is not necessary to do any more processes on that part when they have been fired. After the firing, the body here is coated with a glass solder. That's a glassy paste. Again, it must be dried. And on that paste, we put on a lead frame. Of course, good material here would be Kovar or Alloy 42 because it has a similar CTE as the ceramic material. And in that way, this lead frame is molten onto that body. After that, we have some kind of pre-assembly, and we have the normal process of chip attachment and of wire bonding. Again, for the chip attachment, we cannot take adhesives because process temperatures will be really high. And after we have done the bonding and heating out, we can put on a second glass. That second glass solder is lower melting than the first glass solder. And in that second process, we have a ceramic lid that is brought onto that body. And the soldering temperatures for glass soldering are, let's say, around 500 for the first and maybe around 350 or so for the second glass soldering. In the second process, of course, we do not want to have a temperature that is too high because that would damage the chip or the wire bonds. Okay, that was from theory. I first had that. And then after some time, I was searching for preparation of that lecture. I was searching for examples of packages, but I was not searching specifically for that. In fact, then I got a package and it was that one here. And I took it and I thought, yeah, if you look at it, how is it produced? You think it's a molded package. Then I gave it to our lab in order to cut it. And they did already really hard because they could hardly cut it. And after that was accomplished, it was embedded in that blue material that is just for preparation. So things will not fall apart. And then we did the cutting. And as you see, we precisely have that package we saw here. In fact, that is from analog devices, an acceleration sensor. You can see that from that code here. AD is analog devices, which is or has been one of the leading companies in producing MEMS. And then we had a look inside. Some things were really surprising. First of all, the die attachment, it is really thick. That I had never seen before. Another thing which is, I think, not so good, look at the quality of the sides of the chip. So the cutting definitely was not good here. But that evidently they didn't care too much about cutting. At that time when I saw it, we did not have our project on cutting quality, so also we didn't consider it too crucial. But I can tell you, cutting quality is very important. So what is it here? Finally, we found out that the die attachment is also made with a glass. And the reason is that when you have a glass here, you will not have fumes from thermal degradation. If you would have epoxy and you close that lid at 300 or 350 degrees centigrade, the epoxy will disintegrate, and then you get what? When epoxy disintegrates, what do you get as a result? What are the atoms in epoxy or the elements? What is a structural atom in an epoxy? Yeah, go ahead. Okay. Oh. Evidently I must put some chemical questions in the exam, huh? Okay. We have carbon, we have hydrogen, we have oxygen, and having oxygen and hydrogen together, that means we can create water. Okay. There are other examples of such ceramic packages from preformed things. For instance, that is an example which Professor Stieglitz did together with Dr. Schüttler, who also did his PhD work on that topic. That is an implantable housing for neuroprothesis. So normally in such implants we have titanium shell that has glass feed-throughs. But the target of Professor Stieglitz is to make it smaller. That's one thing. The second is to have more IOs. In fact, if you want to attach some electronics to some nerves, you don't want to just have a single point, but a nerve consists of very many IO lines. So it's like a nerve is not just a line, but it's more like a bus, you could say. Yeah. And in that way, it is better to have many contacts. And so that was their research, having some kind of cable In that case, it was not yet so many, but their main target was to have maybe 1,000 or so IOs for such a part. And again, here we can say that is